Hello and welcome to Toddcast number 59. So continuing on with carbonyls, and it's going to be a reasonable amount of things we've actually covered in the previous alcohol chapters, just organizing them and kind of looking at them from a slightly different perspective. And hopefully that's one thing you notice within both the alcohol and carbonyl chapters, because alcohols get oxidized into carbonyls and because carbonyls can be reduced to alcohols. A lot of what you'll see is in parallel. So the aldehyde forming reactions we've seen before, probably amongst the easiest. We can oxidize a primary alcohol, but because it has two H's to lose, we have to choose a poison. So we looked at it in terms of PCC before. That was one option. So PCC being pyridyl chlorochromate, as mentioned before, and that oxidizes up to just one lost H, the aldehyde. We can also do ozonolysis of an alkene as long as the alkene is not tetrasubstituted. So as long as one of the carbons, and in the case here, this is my H. So because there's an H on this, if I use ozonolysis followed by reductive workup, then I can generate this aldehyde. And then we learn a method in the alkyne chapter. And that was taking a terminal alkyne, using a very bulky boron species to add in an anti-Markovnikov fashion, where you put an OH on the terminal carbon and the H on the neighboring carbon. We end up with what's known as an enol, OH on the alkene, and that can tautomerize into an aldehyde. So we actually have been studying aldehydes without realizing it in the alcohol chapter, the alkene chapter, and the alkyne chapter. So again, this all starts to fit into some sort of network. And if you start seeing this, you get really organized where things fit, you'll realize a lot of what you're going to learn from this point on in OChem is relearning something you already know applied to a slightly different situation, a slightly different molecule. Okay. With that, I also want to consider the fact that ketones can be formed by some of these same reactions. So we can form a ketone by oxidizing a secondary alcohol, just like we did with primary alcohol, up to an aldehyde by losing one H and generating a new bond to O. Same thing in secondary alcohol, it has one H to lose. After we lose it, we convert into a pi bond to O, and we end up with a carbonyl, in this case a ketone. This is known as a Swern oxidation. It was mentioned real briefly before, but going into a little more detail in this case, where you have DMSO, dimethyl sulfoxide, which is like DMS that we do in the reaction with ozonolysis, where it cleans up that third oxygen. So this can serve as a solvent and help in the oxidative process. And then we have this species here, the highly oxidized carbons. And carbon with an oxidation state of +3, which readily wants to get reduced. So as it gets reduced, the ketone is going to get oxidized. So for this system, we use this simply because chromium is highly toxic. So this is an alternative. And so you chaser is triethylamine, which basically cleans up the acidity associated with this compound. So won't go into the mechanism, just want the basic idea that you can oxidize by losing this H. Ultimately, it's going to end up being picked up by a base, and then these carbons are going to get reduced down. Okay, ozonolysis of an alkene, we've already seen that one. And as just mentioned here with DMSO, DMS, dimethyl sulfide, can pick up an O and turn into DMSO. But that's a little side note. We cleave, so exact same reaction we just did for aldehydes, noting that on one side we got an aldehyde, but on the left side, we end up getting a ketone. And then last but not least, we can also do Markovnikov addition to a terminal alkyne. And in fact, it doesn't have to be terminal. I chose terminal to match the previous slide. But if I add the OH to the interior carbon, then the enol is on a substituted carbon, and it can turn into a ketone. So there we have it. Nothing you haven't seen before, but just organizing it. And again, that's going to be a major part of what we're going to do. Do want to look at the general reactivity of a carbonyl then early on. And I'm going to address some topics that are not necessarily covered in this chapter, tying into the big picture. So what I hope you do is you go through these questions, go through these examples, is you set yourself up to be highly organized for the future. And so what I mean by that is generally know what a carbonyl does. So this resonance structure where this carbon pi bonded to this O can undergo a break of the pi bond, form a minor resonance contributor. It carries a negative on the O and a positive on the carbon. It is because of this positive on the carbon, which in the resonance hybrid becomes a delta positive on the carbon, that it's going to be highly electrophilic. So a nucleophile, anything with a lone pair to share, is going to seek out the carbon. When it does this, that's a fifth bond to carbon, so it has to break the weakest bond, which is the pi bond. So that mechanism right here, the nucleophile attacking carbonyl and that bond breaking, is going to be seen over and over and over. So we'll figure out what happens in different reactions, but that is key. So because the carbonyl carbon is partially positive, again, it makes it susceptible to nucleophilic attack. And as mentioned, the tetrahedral intermediate. So when those electrons from the pi bond go up top, you end up with 3 lone pairs and just a sigma bond to the O, and then nucleophile is attached. I used a neutral nucleophile, so it became positive because it lost electrons. We can also use a negative nucleophile, which ends up neutral. All depends on like what reaction it is. So something to pay reasonable attention to is the charge of the nucleophile coming in. Okay, generically done. Now for a little more, I guess, application. Because of that carbonyl partial positive, again, it's a good nucleophile, or good electrophile, excuse me, susceptible to nucleophiles. But this is where I'm talking about see the big picture before you start. So we're only going to cover some reactions in this chapter. So there's carbonyl reactions that will be covered over multiple other chapters. But no matter what chapter you're dealing with carbonyl chemistry, it comes down to 2 questions that you should always ask yourself. Is the other reagent it's reacting with, is that acting as a nucleophile or a base? So the so-called alpha carbon, so I'll introduce that real quickly here. If I have a carbonyl, there is a delta plus on that carbon. But on the neighboring carbon, known as the alpha carbon, one away, this pKa, depending on what it is, going to be around 15 to 18, we'll say. And because of that, it can be deprotonated by reasonably weak bases. Now, it's not totally true. It's got to be a strong base in a definition sense. But as far as what we consider an OChem, it's one of the relatively weaker strong bases, if you will, like an NaOH or KOH or NaH, but irrelevant for now because this is what we'll cover down the road. This H can be deprotonated. So if I add something that's too strong of a base, it's easier to take an H than it is to attack a carbonyl, so it'll deprotonate and act like a base. But if it's weak enough that it cannot deprotonate the H, then it has to default into being a nucleophile. So if it's a nucleophile, let me clear this out. If it's a nucleophile, then just like before, it's going to come in and attack and kick this up. Notice I made the nucleophile negative this time. All depends on what I'm doing. So it's not as important about the charge as it is just as long as it has a lone pair that's capable of attacking. Okay, so if it acts like a base, again, it's going to take off the so-called alpha proton. And by doing so, it's going to kick electron density up. And so you're going to end up with an enolate, as it's called. So an enol, again, has a double bond with an OH. When it's deprotonated, when O's get deprotonated, it ends in ATE, 8. So enol 8 would mean it's an ene with that. But this O can kick those electrons in, and that pi bond becomes a great nucleophile. That's for down the road. So when you see this in the big picture, this is what we're going to do this chapter. Just nucleophile attacking carbonyl with no leading group and just acting as a nucleophile. We're not going to worry about it acting as a base. So we'll consider just nucleophiles, not bases for this chapter, but keep in mind that's going to be down the road. So if you think about it early on, why it's acting this way, that'll help to make the transition to more information easier. And as mentioned, addition as opposed to having a leaving group. That's going to be the second question we ask. If there's a leaving group attached, something that can leave, so let's say this was a chloride, for instance, nucleophile comes in, kicks up, when it comes back in, it kicks the chloride out, and that would be a substituting nucleophile for the chlorine leaving group. Or if there's no leaving group, then it's just going to go on, remain as an anion, it has to get protonated. Okay, so let's look at these in more detail. Here I have the two questions I need to ask. Number one, is an amine a strong base, medium base, weak base? So memorizing these things matters. Ends up amines are weak bases, so it's not going to be strong enough to deprotonate. It has to act as a nucleophile. So consequently, we have a nucleophile. And then number two, do we have a leaving group? Ends up, as mentioned, chlorine is an excellent leaving group. So because it has a nucleophile and a leaving group, the nucleophile is going to attack the carbonyl. It's going to kick up, kick in, and kick out a leaving group, undergo what's known as a substitution reaction. So the combination of nucleophile and a leaving group results in a substitution of the carbonyl. So again, it's going to come and attack the carbonyl, kick up. You get this tetrahedral intermediate. Tetrahedral because the carbonyl has 4 bonds. Well, it has 4 sigma bonds specifically. If that kicks in, could kick out that group and go backwards, but the better leaving group is the chlorine. It's end up with this species. Eventually, there'll be a proton transfer. This isn't your final product, but I'll show this for here. Again, this is going to be future chapters, but knowing the big picture helps. So nucleophile, definitely have to know leaving group. We won't really go into any reactions beyond just this initial one. So let's do this again. We have a CN minus, which we learned in the SN1, SN2 chapter, is a nucleophile, way too weak to deprotonate anything. So nucleophile, check. And this time it's alkyl group, so there's no leaving group, so it cannot undergo substitution as to undergo addition. So second reaction we'll look at, addition across the carbonyl. So the CN is going to attack the carbon, just like nucleophiles do, get the electron pair up, so we have this tetrahedral intermediate. This can't kick in and kick anything out. They're all carbon-carbon bonds, so therefore they're all stable, which means it just has to wait until it can find a proton. So step 1, substitution to form tetrahedral intermediate. Second part, H plus gets added to the O. Last, I have this group. Ends up ethoxide. The alcohol pK is 15-ish, 15 to 16. Alpha carbons, again, are in that, probably stretching it when I take it all the way down to 15. I'm going to say usually around 18 or so. So if this comes in and deprotonates, it's not quite strong enough to make it a favorable reaction, but it's strong enough to be able to deprotonate some of these H's. So when it does, it's going to take away that alpha proton. We're going to form that enolate intermediate. Does it leave group? No. But as it stands, not going to matter in this chapter. But it is going to deprotonate. When it deprotonates it, again, you end up with this. And because of this ability to kick in here, this ends up being a great nucleophile. So the blue arrows show what it can do. So what we'll learn is if there's another compound like an alkyl halide, then it can get a halogen and I can extend the chain length at an R group. Again, not what we're dealing with this chapter, but just want to set this up just so you can see the big picture. Okay, so far so good. So for this chapter, for what we're going to deal with, we are limited to just this reaction. That's what we're going to study, but it is worth your time to start early on in setting this up in a way where you can recognize the big picture, just all the different reactions that could come across your table. Okay, so I'll go ahead and move on. We're just going to specifically look at aldehydes and ketone additions. So I want to consider conditions. It could be basic or it could be acidic. Under basic conditions, we have a tendency to generate a nucleophile. Conditions are deprotonate, make, break, protonate. So in this case, doesn't deprotonate, so it's just going to start with make. Nucleophile is going to come in, make and break. Same thing we did with nucleophiles before. So if it's a negative nucleophile, it'll attack the carbonyl. So make, break, and it has to end with some sort of protonate. So where it comes from, if we have acidic water, the problem I have with this mechanism, I need to be careful. If I have a negative here, then it's going to be a water that typically will be what undergoes proton generation or the proton source. If, however, the nucleophile is neutral, then in that case, I will end up with a positive here. And because of the positive charge, the water can be or the hydronium can be the source, because then you can have a positive charge in that. So in this whole process, O- will pick up an H, and then another water can deprotonate the leading group. So because we're doing the basic conditions, I should stick with something like this picture. So I cross the two up. So in the end, that goes that way, and you end up with an OH minus, a basic condition, and a alcohol. So it turns into OH. And whatever this nucleophile is, that may also have a functional group. It could be an alkyl group, like a Grignard reagent, for instance. We've done that one before. It could be a cyano group, which still forms a carbon-carbon bond that can't leave, or it could be actually something that's reasonable as a leading group. We'll see as we go. Under acidic conditions, protonate, break, make, deprotonate. Generally, more common, especially if you're going on to biology, that'll be somewhat useful for you, because most of what we do as far as enzymatic cleavage, it acts like a Lewis acid, or acidic conditions like in the stomach or lysosomes, we protonate, make things better leading groups. So we're going to protonate, which means acidic conditions need something acidic. So it's going to come in and take an H from an acid, whatever this acid may be. We now have a positive O, so protonate, we did that, break. That's going to break, form a carbocation intermediate. This nucleophile is going to come in. And again, I should probably make it neutral. And so in the end, after it gets protonated, or I should say deprotonated by whatever the conjugate base is. So let me go ahead and leave this as a positive on the nucleophile. And then A minus can come in and deprotonate it, turn it back into neutral species. So we end up getting the same product in both cases. In just one case, protonate, break, make, and then deprotonate. That cation didn't have a neutral or worked up product. In this case, deprotonate the nucleophile, make it negative, it comes in attack, so deprotonate, make, break, and then protonate the water and end up back where you started. So again, we're doing kind of the same mechanisms we did in previous chapters: protonate, break, make, deprotonate, or deprotonate, make, break, protonate. As long as you can just see the overall trend, that's what matters here. So a lot of information being thrown at you that is the same information that you've learned before applied to new situations. So hopefully, as it starts to be a little bit information overload, you can take time to be organized. So these reactions in general, can be done with many different types of nucleophiles. So one is just inventory. We've done waters in nucleophile, we've done alcohols in nucleophile, and when we formed ketals and acetals, we used a diol. So OH on a water, OH on an alcohol, two H's on a diol. Hydrogen's also been in nucleophile. We learned that in alcohol chapter when we dealt with sodium borohydride and lithium hydride, where hydride was a good nucleophile. With carbon nucleophiles, Grignard and cyano groups. So we're going to start adding a few more. So we're also going to learn something called a Wittig reagent later on, where you have a carbon negative charge attacking. This will attack the carbonyl and form a new carbon-carbon bond. We're going to have nitrogen nucleophiles, where we form compounds known as imines, or enamines when they attack carbonyl. We're going to have sulfur. So lots of different species can be the nucleophile in this case. So again, we've done all the alcohols. So we've done water, alcohol, and diol. We've done all the hydrides so far. And we've done Grignard and cyano. So you already know what happens from previous experience with 7 different reagents. So when we start introducing these new ones in 8th, 9th, 10th, 11th, and 12th, so 5 more, see the big picture. So organization is key because there is so much going on in this chapter, so much carrying over from the previous alcohol chapter, that the quicker you can assimilate it into an organized big picture, the better you're going to understand everything. So sorry if this was a little bit chaotic. Hopefully everything fell into place by the end, and that you realize you know most of what we're dealing with. We'll end up doing a lot of stuff repeatedly. Anyway, ends this podcast. I'll get back into the flow of things little by little, but 1 down. I think we have 5 to go. So 59 out. See you for 60 through 64. So have an absolutely wonderful day and see you in the next podcast. Thank you.